Okay, let's start with the fundamentals. Microservices architecture is all about taking a big, complicated application, think of it as one giant block, and chopping it up into much smaller, independent pieces. These smaller pieces are called microservices. Each microservice handles a specific part of the overall business, like user accounts, order processing, or product recommendations. They talk to each other using simple messages, often over standard internet protocols. The coolest thing is that you can update one service without having to touch any of the others, and importantly, different teams can work on different services. They don't all have to use the same technology stack. This leads to faster development times and a much more resilient system. Okay, let's talk about what really makes a microservice tick. Think of them as tiny, specialized units within a larger application. They're designed to be small and independent, meaning each one does just one thing really well. Importantly, they don't need to all use the same tools or technologies. Teams have freedom to pick what works best for their service. Each microservice also has its own defined area of responsibility, like a specific part of the business process. And because these services operate separately, if one goes down, it shouldn't take everything else out with it. They're built to be resilient and isolated. Okay, so let's talk about why microservices are often preferred over the traditional monolithic approach. The biggest benefit is usually increased agility. Teams can work on different parts of the system independently, making development cycles much faster. It also makes scaling a breeze. You only need to scale the services that are actually experiencing high demand, not your entire application. Plus, if one service hiccups, it's less likely to take down everything else, improving resilience. And because each microservice can use different technologies best suited for its job, it opens up possibilities for innovation and keeps things manageable. Okay, let's talk about the big hurdles when you're diving into microservices. It's not just about building lots of small apps, it actually introduces a whole new set of challenges. Primarily, managing all those individual services, their codebases, deployments, and updates can become incredibly complex. Then there are the inherent difficulties of distributed systems, like dealing with potential delays in communication between services and having to handle failures gracefully. Maintaining data consistency across different parts of the system also presents a significant problem. You'll need to think carefully about how transactions work. And don't forget monitoring. Traditional tools aren't always effective at tracking everything that's happening across all your microservices, so you'll need specialized observability solutions. Finally, things like finding and routing requests between services and securing their communication are also important considerations. Okay, let's talk about how these independent microservices actually talk to each other. The most common way is through our REST-default API. Think of it like a well-defined phone call where one service asks another for something and gets an immediate response. But that can create tight links between services, which isn't ideal. Asynchronous communication using message queues, like RabbitMQ or Kafka, offers a better solution by decoupling the sending and receiving sides. Services push messages to a queue, and other services pick them up when they're ready. Event-driven architectures are even more flexible. One service publishes an event saying something happened, and others react accordingly. And for high-performance communication, you've got gRPC, which is similar to REST but uses protocol buffers for speed. Okay, let's talk about how microservices communicate. The most straightforward way is synchronous communication, like making a phone call. One service asks another, and it waits for an immediate answer. It's simple but can lead to problems if the other service isn't available or takes too long. Think of it like a tight connection. Now, asynchronous communication is different. It's more like sending a letter. A service sends a message and doesn't hold its breath waiting for a reply. The recipient processes it later. This method is much more flexible and resilient because services aren't locked on each other. It's the key to building robust microservice systems. Let's talk about how microservices actually talk to each other. There are several common ways they do this. First up is REST. It's the most familiar, using HTTP methods and JSON or XML for data exchange. It's really straightforward to implement. Then we have gRPC, which is a powerful option that's much faster than REST because it uses protocol buffers. For situations where services need to communicate without being directly connected, like handling events, message queues like Kafka or RabbitMQ are fantastic. And finally, GraphQL is gaining popularity as a way for clients to request exactly the data they need from an API, which can really improve performance. Thinking about whether you need synchronous or asynchronous communication and prioritizing performance are important factors when choosing a protocol. Okay, let's dive into API gateways. They're essentially a central hub for all requests to your microservices. Imagine you have multiple little apps working together. The gateway handles incoming requests and directs them to the right service. This simplifies things for clients because they don't need to know about the individual services. It also helps with security, manages traffic flow, and even transforms requests before sending them out. Basically, they make your microservices architecture much easier to manage and use. Okay, let's talk about service discovery. It's a really crucial concept when you're building microservices. Basically, in a system where services can appear and disappear all the time, they need a way to find each other without knowing their exact location upfront. It's like having a constantly updated phone book for your applications. Service discovery is a mechanism. It allows services to locate one another dynamically, avoiding hard-coded addresses and ensuring reliable communication even as things change. There are a few common ways to do this. Clients can directly query registries, or services register themselves with a central system. Okay, let's talk about service discovery in microservices. It's the process of how services find each other without hard-coding their addresses. Several tools are commonly used to make this happen. You'll often hear about Consul. It's a really popular choice, offering a lot more than just service discovery, like key-value storage and distributed configuration. Netflix Eureka was also extremely prevalent, especially in older projects. Zookeeper is another option, primarily because it's a robust coordination service that can manage registrations. And if you're running on Kubernetes, the built-in DNS service is incredibly powerful and convenient. Finally, HashiCorp Vault Agent can be used to dynamically discover services and their endpoints, particularly useful when dealing with secrets management alongside service discovery. Okay, let's talk about configuration servers in microservices. Think of them as the master control panel for all your services settings. Because microservices are independent and often deployed across different environments, development, staging, production, it's crucial to have a single source of truth for things like API keys, database URL, or even which features are turned on or off. A configuration server doesn't change the code in your services. Instead, it provides those settings dynamically so that each service can access them at runtime. This makes updates much easier and faster than having to redeploy every microservice whenever a setting change is hugely beneficial for agility. Okay, let's talk about how we handle data when building microservices. It's a really important area because each service often needs its own database to be completely independent. A popular approach is database per service, which means every service owns its own schema and can choose the most suitable database for a specific job, like maybe PostgreSQL for handling transactions, or MongoDB if you need flexibility with your data structure. Sometimes, a shared database might work, but that needs very careful planning to avoid issues with consistency and security. And frequently, we'll use something called eventual consistency, meaning data won't be perfectly synchronized immediately across all services, but it will eventually become consistent through messaging systems. For more complex transactions that span multiple services, the Saga pattern is a powerful tool. Finally, think about how you'll keep data in sync. Things like change data capture can help with this. Okay, let's talk about a really important design choice when building microservices, the database per service pattern. Essentially, each individual microservice has its own dedicated database. Think of it like this: instead of having one giant shared database that everyone touches, each service is responsible for storing and managing *its data. This offers tons of benefits, including greater independence, allowing services to scale individually and choose the right database technology for their specific needs, all while keeping things more stable if one part of the system has an issue. Okay, so let's talk about the tricky part: managing data when you've broken your application into lots of small microservices. It's not as simple as having one central database anymore. One big challenge is figuring out how to keep all the data consistent across these independent services. We often aim for eventual consistency, which means things might be slightly out of sync temporarily, but will eventually catch up. Then there's transactions. Traditional banking-style transactions are hard to move between different services. Instead, we use patterns like sockets to handle complex operations that need to happen across multiple parts of the system. Because data is spread around, you'll often find yourself duplicating it in places and then figuring out how to keep those copies in sync. Change data capture can be a useful tool here. And don't forget about keeping everything governed consistently as your services evolve. Versioning schemas becomes really important. Okay, so when you're dealing with transactions that touch multiple microservices, which is pretty common, it's a whole different ballgame than traditional databases. The old ACID rules just don't apply as easily. You face challenges like distributed data and eventual consistency. That means updates might not be immediately visible in all services, introducing potential inconsistencies. To manage this, you've got several options. One popular approach is the Saga pattern, which can either orchestrate or choreograph the sequence of steps across services. You could also consider two-phase commit, but be aware that it can create bottlenecks and tight coupling. Finally, if something goes wrong, having compensation transactions ready to undo previous changes is crucial for maintaining data integrity. Okay, let's talk about Sagas. They're really helpful when you're building a system with many independent microservices. Think of them as a way to keep things consistent even though your services aren't all talking directly to each other. Basically, a Saga is like a mini transaction that spans multiple steps across different services. A central coordinator kicks things off, and then each service does its part. If something goes wrong during one of those steps, a payment fails, the system doesn't just stop, it executes compensation transactions to undo any changes that were made. There are two main approaches: an orchestration-based Saga where you have a single control guiding everything, and a choreography-based version where each service listens for events and reacts accordingly. Essentially, Sagas add robustness and make your microservices easier to manage. Okay, so let's talk about consistency in microservices. Traditionally, when you're dealing with transactions, you need ACID properties. All changes must be consistent everywhere at once. But that's really hard to achieve in a distributed system like microservices. That's where eventual consistency comes in. It means that even if updates aren't immediately reflected across all services, the asterisk will asterisk eventually get there. We usually achieve this by using asynchronous communication between our services so they don't have to wait for each other. We also need to make sure our services are output, meaning they can handle the same message multiple times without causing problems. And if something goes wrong during our process, we use techniques like compensating transactions or sockets to roll back any changes and get things back on track. Okay, let's talk about the circuit breaker pattern. It's a really important tool for building robust microservices. Think of it like an electrical circuit breaker in your home that prevents overloads and protects other circuits. In our services, it prevents one failing service from bringing down the entire system. When a service starts to fail repeatedly, the circuit breaker threats stopping new requests from going to that service. Instead, we can provide a fallback, maybe using cache data or a default value so users aren't left waiting with an error message. After a set time, it tests if the failing service has recovered, and if it's healthy again, the circuit breaker resets. Okay, let's talk about orchestration versus choreography. There are two different approaches to how microservices work together. Orchestration is like having a conductor leading an orchestra. One central service tells each individual microservice exactly what to do and when. It keeps track of the whole process and manages state. It can be easy to set up initially, but scaling and handling failures can get tricky. On the other hand, choreography is more like a dance. Each microservice listens for events happening elsewhere and responds accordingly without needing someone to tell it what to do. This makes things much more decentralized and scalable, but debugging can be a bit more challenging. Okay, let's talk about securing your microservices architecture. It's not just about one layer, you need a defense-in-depth strategy. Starting at the front door with the API gateway is key. Think of it as your security guard. We use things like OAuth and JWT to control who gets in. Then, service meshes can add an extra layer of encryption by ensuring all services know who they're talking to. Don't forget about rate limiting to prevent overload, and always validate everything coming asterisk and asterisk to your services. Don't trust the client. Secure communication protocols like HTTPS are a must, and lastly, follow the principle of least privilege. Give each service only what it absolutely needs. Security is something you need to keep monitoring regularly. Let's talk about securing your microservices. When you're building a system with many small, independent services, it's really important to make sure that only authorized entities can access data and functionality. There are several common approaches we use for this. Simple API keys can work well for external access control, but for internal communication, something stronger is needed. JWTs or JSON Web Tokens are a popular choice because they allow services to verify the identity of each other without needing to constantly exchange credentials. OAuth 2.0 lets one service act on behalf of another user, which is super useful when you have third-party integrations. And for really high security, mutual TLS uses certificates to confirm that services are who they say they are. Finally, role-based access control, or RBAC, allows you to define roles with specific permissions and enforce those roles across your microservices. Remember to think about whether you want a central authentication point or distributed, how you revoke tokens if needed, and always follow the principle of least privilege. Give services only what they absolutely need. Okay, let's talk about centralized logging, a really important concept when you're building with microservices. Because each service in a microservice architecture operates independently, the logs are often spread out everywhere. Centralized logging is like having a single place to collect all those logs from every service and store them together. This makes it much easier to troubleshoot problems. You can see how different services are interacting and pinpoint the root cause of an issue much faster. It also helps with monitoring, so you can set up alerts if something goes wrong. Plus, centralized logging provides a great record for auditing and ensuring compliance. Basically, it simplifies log management significantly. Okay, let's talk about monitoring and microservices. It's absolutely key to keeping everything running smoothly. We use a bunch of different tools for this, and it's often best to combine several. Prometheus is super popular for collecting metrics. Think of it like a central dashboard showing how your services are doing. Then, for tracing, we need to understand where requests are going when they hop between multiple microservices. Jaegers can help with that. Logging aggregation tools like the ELK stack, Elasticsearch, Logstash, Kibana and Grafana Loki let us pull all our logs together in one place for easier debugging. Service meshes like Istio or Linker give us even deeper insights into how services are communicating with each other. Finally, real user monitoring RUN tools like New Relic or Datadog help us understand the user's experience and catch any problems on their end. Okay, let's talk about getting these microservices live. First off, we always package each service in a Docker container. It's like creating a little self-contained unit. Then, we use an orchestrator like Kubernetes to manage those containers automatically. Think of it as the conductor of our microservice orchestra. We also need really strong CI/CD pipelines to automate the build, test, and deployment process. When deploying, rolling updates are my preferred strategy. They minimize downtime. We might even try canary deployments if we want to test a new version on a small group first. Crucially, services have to be able to find each other, so service discovery tools like Console or Kubernetes DNS come in handy. And finally, don't forget monitoring and logging. We need to keep an eye on things tracking metrics like response times and errors to make sure everything is running smoothly. Okay, let's talk about containerization and why it's such a crucial part of building microservices. Basically, containers are like tiny, self-contained packages that hold everything an application needs to run its code, libraries, and even how it works. They don't need to virtualize hardware like traditional VM, they share the host operating system's kernel, which makes them much lighter weight and faster to start. Because of this, containers are incredibly portable, meaning your microservices will behave exactly the same way whether you're running them in development, testing, or production. And importantly, they provide isolation, so one service won't interfere with another. Now, why is this perfect for microservices? Well, each microservice can live in its own container, which makes updating and scaling incredibly easy and efficient because changes to one service don't impact the others. Plus, containers are super resource efficient, helping you keep costs down as your application grows. Okay, so let's dive into how Kubernetes comes in for microservices. It's really the backbone that makes this whole approach work. You can think of it as a super smart conductor for your orchestra of tiny services. It handles all the tricky stuff like making sure each service knows where to find the others, no more hard-coding IP addresses. Plus, if one service starts having problems, Kubernetes automatically steps in and restarts it. And when you want to update a new version, Kubernetes manages rolling updates so you don't have any downtime. It's all about automation, scaling based on demand, and keeping everything healthy and running efficiently. Okay, let's talk about versioning and microservices. It's really important because changes to one service can ripple through the whole system. There are several ways we can handle this. One popular approach is semantic versioning using major, minor patch to clearly indicate if a change is breaking or not. Another option is to add the version number directly to the URL, but that can lead to a lot of messy URL. We could also use HTTP headers, which gives us more flexibility, or even content negotiation where clients specify exactly which version they want. Remember, always strive for backward compatibility and have clear plans for deprecating older versions. Okay, let's talk about blue-green deployments, a really smart way to handle releases in microservices. Basically, you're running two nearly identical production environments, one blue, which is currently serving your users, and another green, where the new version of your application is live. You gradually shift traffic from the old blue environment over to the fresh green environment. If everything looks good, you just switch all the traffic over, and the green one becomes the primary. It's fantastic for minimizing downtime, making rollback super easy. You just flip back to blue and it significantly reduces the risk of problems popping up after a release. Okay, let's dive into canary deployments. Think of it as a way to test out new versions of your microservices without taking a huge risk with everyone. Instead of immediately pushing the update to all users, you introduce it to a small group. We call them the canary. You monitor them really closely for things like errors and how quickly requests are being handled. If everything looks good, you slowly increase the number of users seeing the new version until it eventually replaces the old one. It's a fantastic way to catch problems early and minimize disruption. Okay, let's dive into how we can migrate a large, complex application or monolith to microservices. One really effective technique is called the strangler-fig pattern. It's named after the fascinating vine that literally wraps around and eventually replaces the host tree. The idea is simple. We start by identifying a small piece of functionality within the monolithic at something relatively low risk, like perhaps user logins or generating reports. Then, we build a brand new microservice to handle that one function. We carefully start diverting some traffic to this new service, using things like API gateways and routing rules. As we get more confident in the new microservice's performance and reliability, we gradually expand its scope until it completely replaces the original part of the monolith. It's a slow, steady process that minimizes risk and lets us iterate quickly. Okay, let's talk about some common traps to watch out for when designing microservices. First off, avoid what we call a monolithic microservice, essentially treating one of your services like a huge, single application. Then there's the distributed monolith, where you end up with services that are tightly linked through shared databases or external systems, which can create major bottlenecks. Don't go overboard and try to break everything down into many tiny services. Either we call this micro-bloat, and it actually increases complexity. Finally, be mindful of consistency. Immediate consistency across all services isn't always the best approach. Embrace eventual consistency when you can, but understand how that works. And critically, make sure your service boundaries are well defined. Avoid sharing data or responsibilities between services unnecessarily. Okay, let's talk about how we handle things going wrong when our microservices are talking to each other. It's not enough to just try again and again. That can actually make the problem worse. We need strategies in place. One really helpful pattern is a circuit breaker. It stops sending requests to a failing service temporarily, preventing a domino effect. Then there's a bulkhead pattern, which isolates potential problems within one service. We also use retries with a smart approach. Exponential back means we wait longer and longer between attempts. Plus, timeouts are important so we don't get stuck waiting forever. And finally, having a fallback or degraded mode is key. If one service can't do its job, we want to have something ready as a substitute. Don't forget monitoring too. Keeping an eye on failure rates and setting up alerts is absolutely vital. Let's talk about a really useful pattern in microservices called the sidecar. Imagine you have a core service, and you need to add things like logging or monitoring functions that aren't part of the main service's job. Instead of modifying the core code directly, we can use the sidecar. A sidecar is a separate process that runs alongside your microservice, handling these extra tasks. It communicates with the main service over a network, so any changes to the sidecar don't mess up the main service. This keeps things decoupled and reusable, making it much easier to scale everything individually. Okay, let's talk about service meshes. They're becoming really important in microservices architectures. Imagine you have dozens, maybe hundreds, of small services all talking to each other. Managing that communication can get incredibly complex, especially when it comes to security and keeping track of what's going on. A service mesh is like a dedicated layer of infrastructure that handles all the low-level networking details, things like routing requests between services, ensuring they're secure through encryption, and providing detailed insights into how everything's performing. It takes away a lot of the headache from developers so they can concentrate on building features. Okay, let's talk about some of the popular service mesh tools out there. Service meshes are designed to make managing these smaller, independent services a lot easier. Istio is a really big one. It's super popular and has a large community backing it up. Linkerd is often praised for being simpler and quicker to set up. Then you've got Console Connect from HashiCorp, which works well if you're already using Console for service discovery. And finally, AWS App Mesh is a managed option if you're heavily invested in the Amazon ecosystem. When thinking about these tools, it's good to consider what your team needs and how well each one aligns with your overall architecture. Okay, so let's talk about API composition. Basically, it's how we take several smaller microservices and glue them together to create a single, more complex endpoint for our users. Imagine you're building with Lego bricks. Each brick is simple on its own, but when you combine them, you can build something really amazing. This approach simplifies the experience for clients because they don't need to juggle multiple API calls. It also gives us flexibility as we can update individual services without breaking the whole system. Okay, let's talk about the backend for front-end pattern, or BFF as it's often called. Think of it like this: you have a bunch of different apps, maybe a web app and a mobile app, all trying to get data from your backend microservices. Now, each app might need slightly different data shapes or transformations to best display things for its users. If the backend just sent raw data to everything, it would be slow, repetitive work for each app, and make our backend services much more complicated. The BFF solves this by acting as a translator-specific service that's built just for one particular front end. It takes all the necessary data from the microservices, transforms it into the exact format that front-end needs, and then sends it along. It's like having a dedicated helper for each app, keeping things simpler on the back-end and making your front-ends faster and more efficient. Okay, so when it comes to scaling microservices, it's not as simple as just adding more servers. The key is understanding that each service needs to be scaled independently. Horizontal scaling, adding more instances of a particular service, is the most common approach. We use things like Kubernetes to automate this process based on how much traffic each service is receiving. Sometimes, you might need to shard your database if you're dealing with huge amounts of data for certain services, and caching can also significantly reduce load. And don't forget about circuit breakers. They are essential for preventing a single failing service from bringing down the whole system. It's important to identify where the bottlenecks are through monitoring before trying to scale anything. Okay, let's talk about how we make our microservice applications handle more traffic. First up, there's vertical scaling. This is like upgrading your computer with a faster processor or more memory. It's straightforward at first, but it has limitations. You can only scale so far before hitting a ceiling, and if one server goes down, the whole system could be affected. Now, horizontal scaling is a different beast. Instead of making one machine bigger, we add more machines to handle the load. This makes things much more resilient. If one fails, others just pick up the slack. It's more complex to set up initially, but it's generally the better choice for microservices because you get far greater scalability and fault tolerance. Okay, let's talk about CQRS. Think of it like separating your reading and writing habits. Traditionally, a database does both. It handles creating new things commands and also looking up information queries. But that can get really slow and complicated as things grow. CQRS is all about splitting those jobs apart. On the command side, we focus on making sure our data stays consistent and reliable, like when you're adding a product to an online store. That happens in one place with its own rules. Then, for reading information like showing product details, we can use totally different systems optimized just for getting that info out quickly. It's like having separate experts handling each task, allowing us to scale better and build more robust applications. Okay, let's talk about how event sourcing fits into the microservices world. Imagine you have a system where multiple services interact, like an e-commerce application with customer management, order processing, and inventory. Traditionally, all that data would live in one giant database. But with microservices, each service manages its own data silo. Now, how do these services communicate? That's where event sourcing comes in. Instead of storing the current asterisk state of something like a customer's address, we store every single action that changed it, address changed, customer name updated, etc. Each microservice then publishes events when something important happens, and other services listen for those events to update their own data accordingly. This makes the whole system more flexible, auditable, and easier to scale because the different parts don't need to constantly talk to each other directly. Okay, let's talk about distributed tracing. In a world of microservices, it's easy for requests to bounce around, touching multiple services along the way. Think of it like following a detective through a complex case. You need a clear path to see what's happening at each step. Distributed tracing provides that path. It's all about creating spans, which are essentially logs for individual operations within a service. And then these spans get grouped together into traces representing the entire journey of a request. The key is context propagation, making sure each service knows where it fits in the bigger picture by passing along identifiers like trace ID and span ID. Okay, let's talk about testing microservices. It's a bit different than traditional applications. You can't just test the whole thing as one unit. Instead, you need to approach it in layers. We start with unit tests, which focus on verifying individual pieces of code within each service are working correctly. Then we move on to integration tests, checking how these services communicate with each other, whether that's through API calls or message queues. Contract testing is super important too. It ensures everyone involved knows exactly what to expect from each other. End-to-end tests simulate the user's journey across multiple services. And finally, chaos engineering, where we deliberately introduce failures into the system to see how resilient it is. Remember the test pyramid. You want lots of quick unit tests, fewer integration tests, and even fewer end-to-end tests. Okay, let's talk about contract testing. It's a really useful tool for microservices. Think of it like this: each service is an expert in its own domain, and we want them to communicate reliably without stepping on each other's toes. Contract testing helps us do that by establishing clear agreements between services, what they expect from each other and what they deliver. It's all about defining those contracts upfront, usually as executable specs or schemas, and then having the consumer service verify that the provider actually delivers as promised. This early validation catches issues before they become major headaches during full integration testing, making it easier to deploy services independently with confidence. Okay, let's talk about how applications are structured. It's a big topic. We start with the simplest approach, a monolithic architecture. This is like one giant program where everything lives together. It's easy to get started with, but as your application grows, scaling and making changes becomes really difficult. Next up is service-oriented architecture, or SOA. SOA breaks things down into reusable services that talk to each other, which is a step in the right direction for maintainability. But it can still become complex over time. Finally, we have microservices. These are smaller, independent units of code that do one thing really well and communicate with each other. They're super flexible and scalable, but they also introduce new challenges around managing everything independently. Okay, let's talk about CI/CD pipelines for microservices. They're absolutely essential. Think of continuous integration as making sure every code change gets built and automatically tested. Then we have continuous delivery as the process of getting those builds out to your environments quickly and reliably. And critically, we use infrastructure as code to manage our service and other infrastructure using code itself, which makes things much more repeatable and scalable. We'll look at some popular tools like Jenkins, GitLab CI/CD, GitHub Actions, and Circle CI. Each has its strengths. A good strategy is usually a multi-stage pipeline, with stages for building, testing everything from unit tests all the way to end-to-end checks, followed by staging and finally deploying to production. Okay, let's talk about keeping your microservices API safe. Because they are all spread out and talking to each other, you need some specific security measures in place. First off, think about protecting the gateway that's often the first point of contact. Use strong authentication methods like OAuth or JWT to verify who's asking for access, and then make sure those requests are properly authorized. Next, consider mutual TLS. It's a way for microservices to prove they are who they say they are when communicating with each other. Don't forget about rate limiting, as stops attackers from overwhelming your system. And always validate everything coming in and encode sensitive data leaving. Finally, implement regular security audits and penetration testing just like you would with any other important system. Okay, let's talk about migrating from a big, monolithic application to microservices. It's not just about splitting the code, it's a strategic approach. First, you want to really understand your business. What are the distinct areas of functionality? We use domain-driven design to identify these bounded contexts, which become your starting points for building individual microservices. Then, this triangular fig pattern is helpful. You gradually replace pieces of the monolith with new services, like wrapping it up. Start small with features that aren't overly complex and have minimal dependencies. This builds momentum and gives you experience. It's important to decouple these new services carefully, ensuring they can work independently. Finally, remember that microservices often communicate asynchronously through events, so accepting eventual consistency is key. Okay, let's talk about when it makes sense to go with microservices. They are not always the best solution. First, think seriously about how complex your application is. Lots of features and frequent updates. That asterisk could be a good sign that they might fit. Then, consider your teams. Microservices work really well when you have independent groups who can own their pieces. Scalability is another key point. If certain parts of your app need to scale differently, then it's worth exploring. Also, remember that different services can use different technologies, which is a big advantage. But be aware that this complexity increases the operational overhead too. You'll have more deployments and monitoring to manage. So really weigh up these factors before diving in. Thank you for watching.